In this video, we're going to unpack the phase angle and discover how the value of the phase angle describes the differences between the input function and the output function in the frequency response. We'll also talk about how to compute the phase angle. The phase angle essentially shifts the sinusoidal input in time. A phase angle greater than 0 means that the output function will lead the input function. An example of a phase angle greater than 0 is shown in the dotted line on this plot, where changes in the output signal occur before the similar changes in the input signal. A phase angle of less than 0 means that the output signal lags the input. And that's shown in the broken line in this plot, where after the input signal reaches its peak, the output signal reaches its peak. These shifts are minus pi over 4 and plus pi over 4 radians. We need to be careful when computing the phase angle using something like the arctangent of I over r. The arctangent is supposed to be the inverse of the tangent function, but there's a computational problem with the arctangent because it is not unique. The tangent function has discontinuities that are pi periodic. There's one at pi over 2, one at minus pi over 2, one at 3 pi over 2, etc. So the arctangent is actually a multi-valued function. And in fact, for any argument, there is an infinite number of corresponding arctangents that are separated by plus or minus pi. Since there are an infinite number of answers, the convention is to choose the value closest to 0, that is, the value between minus pi over 2 and pi over 2. What we really want is the phase angle, and the phase angle can be thought of as the polar angle on the complex plane of the point r of s and j I of s. That is, it is the angle made by the real axis and the line connecting the point in the complex plane with the origin. Calculating the phase angle using the arctangent of I over r works fine for calculating the phase angle of the blue point shown in this plot. And that's because the point lies in the first quadrant, where both I and r are positive. However, if either I or r or both are negative, then there's an ambiguity. For example, if the real part is negative, we mean to compute the phase angle for the point over here, but the arctangent function will confuse that with the point here, because the argument I over minus r is equal to the argument minus I over r. And the convention of the arctangent function is to select a value between minus pi over 2 and pi over 2. The phase angle here is greater than pi over 2. There are two functions in MATLAB that can resolve this. One is called the atan2 function, and many other programming languages have a similar function that takes two arguments. The two-argument arctangent allows us to specify whether I is negative, or r is negative, or both are negative. In MATLAB, we can also use the angle function to find the phase angle, where again we can specify the real and imaginary components separately. However, this will still only allow us to compute phase angles between minus pi and plus pi, and we will encounter phase angles that are greater than pi or less than minus pi. So we should be careful when using an arctangent to compute a phase angle, and remember that the phase angle is only equal to the arctangent when it is between minus pi over 2 and pi over 2, or the phase angle is only equal to the two-argument arctangent when it is between minus pi and pi.